Today we have Dr. Kurt Zeidler with us. He is the principal and co-founder of Gall Zeidler Consultants, and he has more than 40 years of experience in the field of tunneling. Um, he has experience in geotechnical engineering, project management, design, and design checks of underground construction and slope stabilization projects. His primary expertise lies in the design of modern excavation and support systems for the tunnels, underground stations, and caverns in hard rock and soft ground in urban areas. He has experience worldwide, and he has been also called upon as an expert consultant for the project in United States, Europe, North America, the Middle East, Australia, and Asia. So it is a pleasure having you, Dr. Kurt, on our platform. You may now start the webinar, Dr. Kurt.
Thank you very much for this kind introduction and the nice invitation which I received some time from you. What I will do today is I will introduce an overview over a big, large project which is currently taking place in the UK. It's the HS2 high-speed 2 railway, which is a mega project also in international scales. And you can imagine that in such a short period of time, or such a short webinar, I can't really talk about all the details, all the individual details, but I will try to give you a fair overview and also pick out a few specific things which may be of interest to you. In general, the entire HS2, do you see my cursor? I hope you see my cursor here.
Yes.
HS2. Excuse me?
The screen is visible. The cursor, can you just move your cursor because it's not visible? Yeah, now it's visible, yes.
Okay, right. So the entire project is broken up into 3 phases. Actually 4 phases, to be honest. But phase number 1 is the phase which with the longest stretch of alignment, and that's currently underway in terms of construction and final design. It connects London to Birmingham and a short stretch towards the north of Birmingham. And from there on, then there is the so-called phase 2A, which is currently in planning and design, relatively far developed design already, all the way up to crew. And then from there on, there is the phase 2B, which finally will take HS2 into Manchester and then connect to existing main railway lines. Phase 2B is phase 2B is actually split into 2 alignments. I just told you about the phase 2B between Crewe and Manchester, and the other branch of phase 2B starts at Birmingham and goes all the way up to Leeds, and then further beyond Leeds again to connect into existing main railway lines. You see a few wiggles here and there. These are typically connections from the new alignment, from the new line to existing railway lines. Just a very brief overview, the estimated cost for the entire phase 1, which is this part here between London and Birmingham, is about 35 to 45 billion pounds sterling, and that includes contingencies of 9.6 billion pounds. These, I have to say, these are all estimates based on some previous estimates. The final costs are not known yet because we are still under construction. Phase 2A, which is the stretch between Birmingham and Crewe, is estimated for 5.2 to 7.2 billion pounds sterling, and the two branches for phase 2B, there is no estimate available at the moment. The phase 1 between London and Birmingham is expected to start services between 2029 and 2033, whereas phase 2 will follow relatively shortly after that and will start latest in 2034. The other branches, there is no estimate available yet. There is, of course, always the question why building such a big mega project, which costs, of course, a lot of money. You see these numbers, they are quite big. And there must be a benefit as well. And the benefit is estimated at the moment based on an estimate by the Parliament of 4.34 billion per year. And this benefit comes from agglomeration of businesses, which means businesses are now closer together in terms of the time it takes to connect between the two businesses or between the businesses. And also the cutting out the time, of course, means it's a reduced time consumption, and that reduces the cost, of course, as well. And this is also expected to increase the labor force participation in the cities along the alignment. If once the full network is in place, it is expected that 13.3 billion will be the accumulated benefits per year provided by the new line, the new high-speed line. There is another report which is slightly more optimistic, which says it's a bit more, 15 billion per year. But as I said, these are all estimates at the moment based on a series of assumptions, and all these numbers need to be verified over the next 30, 40 years. Some further basic numbers for phase 1. I just reiterate, phase 1 is the stretch between London and Birmingham. There are 500 bridging structures in total, 50 viaducts with in total 15 kilometers length. The longest of the viaducts is the Colne Valley viaduct, which is about 3.4 kilometers long. That's part of the contract C1, and I will come back to the contracts a little bit later. And then there is the Delta Junction north of Birmingham. You see here there is a junction here between Birmingham north and then over to the phase 2B, and this includes about 9.5 kilometers of bridges, viaducts, and so on. And this crosses over railway lines, over roads, rivers, and also the M6, which is a major motorway up there. Just to look a little bit more in more detail of phase 1. Phase 1 is broken up into 7 main contracts. The 2 southern contracts, S1 and S2, are basically within the area of London. Then there is the central area with C1, with the Hilton tunnels, C2 and C3. And then in the north, it continues with N1 and N2, which is the northern branch of the northern extension of the of HS2. S1 and S2 are awarded to one single contractor, JV, whereas C1 is one single contract for one contractor JV. C2 and C3 are again awarded together to one single contractor joint venture. The same as is for N1 and N2. Just a summary on the main stations of the alignment. And again, I'm referring to phase 1 now because that's the stretch which is currently under construction. Houston Station is, of course, the biggest station on the scheme, and it will, once it's finished, provide the UK's longest concourse with 300 meters length. It will accommodate or serve 17 high-speed trains per hour. And the plan is to build the main station itself in one construction stage. There are currently enabling works going on there, but the station itself, which is accommodated in a huge box and some connections to existing London Underground stations, this will all be done in one construction stage. As I said, it's primarily cut and cover, but there are also some mined tunnels connecting the new station to the existing stations. It is expected that about 3,000 jobs will be generated by the construction of this station. The cost is estimated 2.6 billion. The Old Oak Station is the next one towards the north, which is also started construction by now. They want to accommodate 14 platforms, and the station, the station box itself is 850 meters long, with all the ancillary rooms, and the construction costs are estimated to be 1.6 billion pounds. The next station further north, next main station, I have to say, is the Solihull station, an interchange station, which provides not only access, of course, to the high speed, but also there's a automated people mover being constructed, which connects this station to the National Exhibition Centre out there, as well as to the Birmingham airport. Also there, the construction started. It will house 4 platforms for the high-speed rail, plus, of course, the platforms for the automated people mover, and the cost will be in the order of 370 million pounds. And the last station, main station in phase 1 is the Curzon station in Birmingham. Also there, the construction started already. It is supposed to be a landmark station. It will house 7 platforms, and the cost will be in about 370 million. That includes the rehabilitation of the existing and adaptation of the existing station, as well as some regional redevelopment plans. And we are tunnelers, and we want to talk about tunnels, of course. And here are the main tunnels between London and Birmingham. The Euston Tunnel, which is belonging to the contract S1, is the most southern tunnel, just outside of Euston Station. It's about 7.2 kilometers long, and connects Euston Station to the Old Oak Station, Old Oak Common Station. And it's a twin TBM tunnel with SCL cross passages, and the diameter is 9.5 meters. Estimated cost are 740 million. And the Northolt Tunnel is 2, and both tunnels are being constructed by the same contractor. The Northolt Tunnel is about 13.4 kilometers long, and that's starting just north of Old Oak Station, Common Station, and then leads up to West Ruislip. It's again a twin TBM tunnel with SCL cross passages, SCL is equals NATM. I have to probably explain that. And 9.5 meters diameter is the tunnel, and the costs are about 1.1 billion pounds. The Chiltern Tunnel is the most southern tunnel in the central section, and it's also the longest tunnel with the highest cover or overburden above the tunnel, about 16 kilometers long with 90 meters cover. And there is
You're on mute, I think. Could have accidentally muted yourself.
Do you hear me now?
Oh yes, loud and clear.
When did I get out of this?
Just at the start of Chiltern Tunnel, I think.
Oh, okay. Start of Chiltern Tunnel. Okay. The Chiltern Tunnel is the most southern tunnel of the central section. It's also the longest tunnel with 16 kilometers length, and it's got up to 90 meters overburden above the tunnel, and up to 30 meters of waterhead. Sorry, this is a typo here. It should be a 30 meters waterhead maximum. It's a twin TAIym tunnel with 38 cross passages constructed using SCL. And I will come back to more details about this tunnel afterwards. The diameter is 9.1 meters, and the cost of the total cost of C1, and that includes the Colne Valley Viaduct, which is the longest viaduct along the route, is 965, it's just below £1 billion. Now, a brief on the geology along the alignment or along the tunnels. The main tunnels, as I said, C1 and C2. Okay, sorry, there's something wrong here. Okay, so let's start again with the S1, with the most southern tunnel, which is located in the typically London geological series with made ground at the top, then London clay. There is, along these alignments, there is no river deposits. So the made ground sits on top of the London clay, which is a highly over-consolidated hard clay. Below the London clay, there's the Harwich Formation, which is cohesive and granular soil, typically water saturated and hence unstable without being treated or dewatered. And below that is the Lambeth Group with cohesive and granular soils, again, highly over-consolidated with pressurized groundwater, which means that the aquifer is confined. And there are actually several confined aquifers in there with quite high pressures up to 140, 150 kPa. The Northolt Tunnel is roughly located in the same geological strata. There is basically no change there in terms of the geological challenges. The Chiltern Tunnel then again is located in chalk, Cretaceous chalk, and I will, as I said, I will come back to the Chiltern Tunnel in more details afterwards. But in general is chalk with various degrees of weathering. Then there are deep dissolution features in the chalk with soft infill. Some of them have soft infill like soft clay. And there are fault zones, and groundwater head, as I said, is up to 30 meters. And the C2 and C3 tunnels are cut and cover tunnels, cut and cover green tunnels, and they are primarily in alluvium, glacial till, limestone, oolites, and mudstone or marlstone. And then the northern Itchingwood Tunnel and the N1 and also the Bromford Tunnel. They're both primarily located above the Mercer mudstone. There are other layers, but the tunnels themselves are primarily located in Mercer mudstones and other at various degrees of weathering. I would like to pick out, as I said, this gigantic mega project. You can't really talk about everything and every individual project and contract and challenge along the alignment within the short period of time. So I picked out three tunnel examples, I have to say. Two of them are major tunnel projects, and the other one are small tunnels, but are also quite challenging. Let's start with the Chiltern Tunnel C1. You see on the right side, you see here the alignment, the approximate alignment, and those pin needles, they are indicating the cross-passage locations. As I said, it's a twin-bore TBM tunnel. The machine is both machines are on the way now. They are both variable density machines. The excavation diameter is about 10.3 meters, just below 10.3 meters, and the TBM shield length of each of the machines is about 16 meters. The internal diameter is 9.1 meter. The segmental lining is built up of 7 + 1 segments, and the ring length of each ring is 2 meters. As already mentioned, the cover is up to 90 meters. There are 3 intermediate shafts which are used for both ventilation and intervention. And as a specific challenge, apart from the very much varying geology along the alignment, both portals are relatively shallow, so the launch or the reception of the TBM take place under very shallow cover. But I will come back to that later as well. The cross passages will be built using TAIym or SCL principles. I will also talk about those cross passages a bit more because there's a lot of additional requirements, not just tunneling. The design speed for the tunnel is 360 kilometers per hour, and the construction works for the shafts, portals, and the tunnels started in 2020. The TBM launch was last year in May, on the 12th of May, so almost a year ago. Progress is very well there, very good there. No major incidents so far. As to the geological settings of this tunnel, the entire tunnel alignment is within Cretaceous white chalk with flints. The flints pose their own challenge to the TBM in particular. The superficial deposits on the top above the chalk, but we are only touching those at the north portal. So otherwise there is the chalk at various different levels of weathering from fresh soft rock to completely disintegrated soft soil, residual soil material. On the right side, you can see here we have broken up the geology along the alignment into behavior classes, in general following Hoke et al., but the class number 4 is, of course, not included in whole canal because it's soil or soil-like material. But we have also correlated this with the Syria grades for the chalk. And you can see what behavior is, rock mass behavior is expected during excavation. But bear in mind, this is always related to unsupported phases, to open phase excavations. This is not related to TBM excavation where phase support, phase pressure is being applied. We've created a tunnel band with the expected behavior and expected geology along the alignment, starting at the south portal here. The south portal starts actually slightly further in here, relatively close to the M25, a major ring motorway around London, which is very sensitive to any disruption, of course, you can imagine. And from there on, then the alignment dives down into better chalk in more structured chalk with behavior class 1 or 2. Then we are crossing underneath the River Misbourne with relatively low cover, and in particular you can see this line here, this reddish line, which delineates the bottom of the structureless chalk. So the structureless chalk is, of course, going to the weathering is going to a deeper, to a greater depth below the River Misbourne and encroaches on the tunnel alignment. This is the tunnel alignment here. And then the alignment rises up again. I have to say that originally the alignment was much deeper. The original alignment before the contractor started on the contract, the alignment was deeper in this area in particular, but it has been raised for various reasons. One reason is, of course, to make the shafts, this is one shaft location, to make the shafts less deep, but also to reduce the groundwater pressure, the groundwater head onto the tunnel. We are crossing the River Misbourne several times because it's meandering at the surface. So this is another river crossing with, again, a T-bex deep weathering pocket. And then we are carrying on with a rising alignment towards the north portal, which is roughly here. And just before the north portal, we are entering a deep pocket of clay. It's clay with flints. It's basically residual soil, completely weathered chalk, very soft in places. And it's also quite challenging for the TBM there because you can imagine when you hit flints, which are very hard in soft material, this is quite a significant challenge for the cutter head, so that you avoid over extraction from the ground. Picking out a few specific challenges or locations of specific interest. I mentioned already the south portal just starts south of the M25. This is the alignment of the M25. This is the south portal. The M25, of course, has, apart from several utilities, also these gantries for signs, road signs, which are very sensitive to ground movements. And the same applies for this to this overbridge here. This overbridge has been already classified as vulnerable, but we were able to reduce the settlements caused by the TBM drive sufficiently so that there was no further damage made to any of these structures. The original South Portal location was much closer to the M25, but the contractor decided to move it as far as possible away from the M25 to have an earlier launch and hence have a longer section of tunneling to get through the learning curve, which you always have when you start at TBM. There's always a certain learning curve in order to stabilize the phase pressure and also the extraction of the ground. So that was a very wise decision by the contractor to gain a few meters, about 100 meters more on excavation length before he crosses underneath the motorway. Additional support measures at the portal were a soil nail wall, which you can see here. It's not very clear to be seen here, but it extends on the sides where these erosion protection mats are. This is all shotcrete facing. And also there was a grouted steel pipe umbrella built around the roof of each of the drives in order to minimize the settlements. And of course, strict TBM control is one of the most important features there when you drive through settlement and ground deformation sensitive areas. And this is just showing here the pipe umbrella which has been installed in order to protect the ground above from deformation or to limit deformations. And this is a section through the soil nail wall at the South Portal. The North Portal, here you can see we are driving through a very deep weathering pocket filled with clay, with flints. And in addition to that, we have a high voltage line crossing the alignment here. And we have two pylons not far away from the actual tunnels. This is the tunnel center line. So there was a long discussion about what we can do there in order to protect those pylons. The initial thought was we could move those pylons out of the way as basically realign a high voltage line. But it turned out that this has been done just recently, a few years ago, in expectation of a different alignment. The alignment has been changed since, so the pylons were moved right in the wrong place, unfortunately. So we couldn't again request a move of the pylons. So we had to introduce soil treatment, deep soil mixing in the area to improve the soil. And then here is the future portal, North Portal. I mentioned already that there are 38 mined cross passages. And of course, these cross passages have to follow, the spacing of these cross passages have to follow certain regulations. The NFPA 130 is the base guideline for that. And hence the opportunity to move cross passages or even to omit cross passages was relatively small. So we had to deal with bad chalk quality no matter what. So we have to basically treat the chalk. And this is one of the examples where we have a cross passage here and another cross passage here, where we are just below the river Mistborn. There is, apart from, of course, the TBM needs to be very strictly controlled in these areas. We had to do ground improvement, or will have to do ground improvement, I have to say, because the first cross passage construction starts actually today. So we have to do ground improvement around the cross passages. This is indicated by this green zone here. for groundwater cutoff primarily, not so much for improvement of the ground strength. That's a side effect which is good, but it is primarily groundwater cutoff. This is a 3D presentation of one of a typical cross passage. It looks like you have the cross passage here. You have an internal collar, and I will come back to that later. And you have a connection detail here with the waterproofing, the inward, and this is now a few sketches. You see the breakout has to take place from the small opening within the TBM, and then it has to be enlarged upwards to gain the full cross passage cross section. Then the excavation will progress across here. Then the enlargement will be done on this side, and then the excavation will turn around and finish this collar section here. On the left side, you see the proposal of what the grouting pattern will be. You see there is an enormous amount of grouting work to be done in order to achieve the permeability, the limitation of permeability to 5 times to the 10 to the -7. You can see there is a lot of perforations also required through the segmental lining. All these perforations have to be plugged afterwards on a permanent basis to make sure that, first of all, these plugs stay in place, and secondly, of course, that there is no water leakage happening afterwards. This is a typical construction sequence of a cross passage. You can see here again, this is the opening which is available for the breakout itself and for the installation of any pre-support from within the tunnel. You see that the pre-support is installed from within the tunnel only in the area which will be removed in future. So that's the segment we are cutting into 2 rings into 4 segments. After testing that all the ground treatment was successful and the installation of the pre-support, the breakout will take place, as I described before, with steps here in 1 meter length, approximately, starting with the transition upwards and outwards, because we have to enlarge from this size horizontally outwards to this line here, and of course upwards as well as downwards. This is the next step, basically continuing the excavation to the other side, to the other tunnel, and the cross passage construction will be carried out only from 1 tunnel, and then we turn around and will excavate the remaining part of this enlargement here, which we didn't excavate in the first step. On the right side, you see a very fresh picture, fresh off the press. These are these internal collars or internal support frames for the openings, which are permanent support frames, which are in this case already, which is already finished in this case, and we break out within this collar. So we cannot use any more space than this here for the breakout, as well as for equipment and material access. This is just a typical longitudinal section with the main elements. You see, this is the frame which you have seen before on the photo. This is the opening, the actual opening in the TBM tunnel, and then we have the waterproofing. There's a shotcrete on the outside, of course, the waterproofing with specific interface details, where the waterproofing is then connected to the backside of the TBM lining. The next example is the Bronzen Tunnel, which is in the north, close to Birmingham. It's about 5.8 kilometers long, and it's a twin-bore TBM tunnel, like all major tunnels along the HS2 alignment. The excavation diameter is 8.25 meters, and the internal diameter is a bit more than 7.5 meters. The ring length is as well 2 meters, and the number of segments is 7 + 1. So it's very similar to the C1 design. There are standard and heavy segments here, depending on the overburden on the cover. In the shallower sections, there are heavy segments, and in between there are standard segments with special segments in the where cross passages are. These are demarking the cross passage, the 13 cross passages. There's one intermediate shaft. This is located here, and both portals again are very shallow, but they are accommodated in the cut and cover structure. The design speed for this tunnel is slightly low, it's 230 kilometers per hour. Construction for the portals has started in 2020, and for the shaft and the TBM will start later this year. It's currently, I believe, being delivered. The geological setting along the alignment, in general, it's Mercer mudstone. There are fault zones, and there is what is a specialty of the Mercer mudstone. There is some swelling pressure. The swelling pressure is assessed to be about 50 kPa in the vertical direction, and the swelling pressure is primarily due to relaxation of the ground, of the rock. So it will expire. It's not like swelling and ongoing. It's not expected to be an ongoing process. However, it will affect the tunnel lining. The groundwater levels you can see here are generally above the alignment, above the tunnel. Sometimes the groundwater is slightly deeper, but still, in general, it's more or less at the bottom of the superficial layers, at the top of the Mercer mudstone. One specific challenge along this alignment is the underpass underneath the viaduct for the M6 motorway. You can see here that's the viaduct with all the bends and the columns and supports, and the tunnel crosses in a very shallow angle, at a very shallow angle underneath this viaduct. Here are a couple of cross sections. The viaduct is founded on pile foundations. The piles don't go very deep because Mercer mudstone is relatively close to the surface, which is good, but still there will be effects on the viaduct. And there were quite, first of all, there have to be done certain protection measures to the bridge, to the viaduct itself. But there is also very strict settlement requirements, settlement limitations, as well as very strict requirements to monitor the TBM and the related settlements to the TBM excavation before we get to the viaduct. And last but not least, a much smaller tunnel, much smaller tunnels, but quite challenging. This is in the middle of London. This is. I'm sorry. Excuse me. There is. It's part of the enabling works for the Euston Station. The Euston Station will be excavated in all this area here. You see these piles coming down here. This is basically the boundary line of the Houston station, and it will take out an existing ventilation shaft and existing ventilation tunnels for the existing London Underground station there. So these two tunnels are quite short, small, but the interesting feature here is that they are the shafts go to about 40 meters depth, but the excavation of the station afterwards will be such that the entire area will here excavated down to about 1 meter above the tunnel roof. So the tunnels will be constructed. They are constructed already. So they are finished, and they're finished under the normal overburden load. During the future excavation for the station, there will be an unloading of that because the entire ground material will be removed above those tunnels. And then the design loads to be taken into account for the design of these tunnels is then that it's about 40 stories design loads acting after unloading the tunnels. They will be reloaded with about approximately 40 stories load. That's the design loads there. The construction takes place in London clay, typically for London. Only the shafts reach slightly into the Lambeth group here and here. These are a couple of pictures from the construction site where you can see the access shaft. There's a temporary access shaft with segmental lining with as a caisson shaft basically. And at the bottom of the shaft, there is an enlargement because of the constrained space available at the surface. They started with a smaller shaft and had then to enlarge at the bottom. And this transition, this enlargement has been done with shotcrete. Another impression from the small tunnels, and I told you about the very, very onerous design load cases, which leads to very heavy reinforcement, in particular of the inwards, but also of the arched and laid down. And you can see here the reinforcements. They are B32s, so that's quite significant, quite a significant reinforcement, which you normally would not see in a normal tunnel under normal conditions. So that takes me to the end of my brief on HS2. Thank you for your attendance, and your questions are welcome.
Hello.
Yes.
Thank you, Dr. Kurt, for your wonderful lecture. So, any questions from our audience?
No questions. Either nobody understood me or it was everything clear. I don't believe that.
Okay, so over to you, Mr. Ayush.
Thank you, Dr. Kurt, for such a wonderful presentation. It would definitely going to help all the young tunnelers while doing the tunneling in their respective countries. I would also like to thank here to all the participants today who joined this wonderful presentation, not only from India, but from Britain, from UK, and from other tunneling industries also. So I think Akhilesh want to ask something, Dr. Kurt. Akhilesh, over to you.
Yeah, I just wanted to. Hi, Dr. Kurt. I'm Akhilesh. I'm from tunnels. Just wanted to understand, like, the diameter of the tunnel for this high speed is 9.1 meters, right? So, just wanted to understand that is there any like special consideration why we are going with the higher diameter?
You've seen that the diameters are not the same at all contracts, and that's not only to do with contractors experience, but it's also aerodynamics, where aerodynamics and the alignment, I have to say more actually. You can see there's a larger diameter for higher speed tunnels, and these diameters are all defined by aerodynamics requirements, and of course utilities, and also the space, the dynamic clearance envelope by the trains when there is when they go around a curve. But the tunnels are really designed to more or less fit those requirements, not any larger requirements or any larger tunnels.
One more question, like what is the minimum curve length of this tunnel? Like,
oh, you got me there. can't tell you, but if you, I can put it, take a note here. So there's the minimum curve radius you're asking for.
yes.
So I will find it out for you. I'm sorry, I don't know that at the top of my head.
No issues.
Dr. Kurd, this is Rajesh here. Actually, I'm sorry I got this information very late, almost at the end of the lecture, that what you are going to present, and it was very interesting in the last minutes. But can I request you, if it is your lecture, somebody was making a recording also, whether this recording will be available to see afterwards also, so that we can understand more. At least I'm very much interested to know more about your lecture. So is it possible to share some slides or lecture?
Mr. Rajesh, we will share this complete presentation on YouTube, and the link I will share with you.
Oh, excellent. And of course, then we have an opportunity to ask Dr. Kurt afterwards also, yeah? Some emails via email.
Yeah, you can mail it to us, and once we get all the questions, we'll consolidate it and send it to Dr. Kurt, and then get back to all of you.
Excellent, because I was also working for Rohtang Tunnel before this, so I'm basically a tunnel engineer, so it's very interesting to know about this more information. Thank you very much.
You're welcome.
One question from my side, Dr. Kurt. When we are driving our TBM drive length was 16 kilometers, was seeing that the length of the drives was 16 kilometers, and the lengths are very, very high. So is there any requirement that we have to provide evacuation shaft in between the tunnels?
Not during the construction.
Okay.
But there is a safe, what do we call a safe haven, just next to the TBM, where the miners, the operatives can have a safe place, safe location when there's a fire or some fumes or something, that they can go in. This is an isolated container where they can. It's a rescue container basically, where they can be.
Okay. Thanks, Dr. Kurt. Any more questions?
Yeah, a small question from my side. Dr. Kurt, I can see behind you on the picture the segments of the lining of the tunnel. There was an exploration for using the PP fibers in place of reinforcement, because it is in the research still whether we can replace the reinforcement with the fibers in the segments. So is it done in this tunnel or not?
Yes. Some segments are highly reinforced. That's the segments around the openings, where the connection to the frame is required, of course. But other than that, there are steel fiber reinforced segments.
Oh, great! That's interesting. That's good. Thank you.
By the way, the background picture is not that tunnel. It's another tunnel in Singapore. Sorry for misleading you. Much smaller tunnel in a different place.
No, at least my question is answered. Thanks for that.
Yeah,
thanks.
thank you. I've seen that somebody's Johnny sent a message here. Is there any particular dowel or bicon used in the segmental lining circumferential joints connecting for cross passages? No. we are using dowels and bicons, but not for replacing any support at the openings for the cross passages. The internal frame, which I've shown to you a picture, the internal frame is the permanent support around the openings. The answer.
Devik wants to ask something. Devik, are you here?
I might as well throw in a question. Kurt, are there any significant initiatives to reduce the captured carbon, or any significant initiatives to reduce the lining thicknesses when compared to the reference design that you might want to highlight?
The lining thickness has been slightly reduced. That's correct. I know that there are currently some research and investigations going on for the southern tunnels to use for sprayed concrete, to use not cement concrete, but a resin bound concrete or sprayed concrete. There are a few other measures or other investigations going on around some proposals by some UK companies, but nothing really specific which is actually being placed at the moment, at least not to my knowledge.
No, thanks.
Hi, Dr. Kurt. I have one doubt. So in India, what mostly I have seen is that when there is a cross passage, they provide a full circular ring around the excavation where they want to start excavating the cross passage. And in your presentation and most of the projects I have seen from in the UK side, that they provide a collar section. So
Yeah.
what are the advantages or disadvantages of any of these things?
The advantage is you don't, when you provide somehow the support around the future openings, when you provide that as part of your lining design, then you don't need a temporary frame. As far as I understand, if I understand you correctly, you were referring to a temporary frame in the area where that is not necessarily not necessary anymore, and the contractors prefer actually to go without a frame because it first of all constrains them in terms of the space available. Depends on the size of the tunnel, of course, but it reduces the space on the inside of the tunnel. Secondly, it constrains the contractor when additional measures have to be carried out, like grouting or ground freezing. I'm currently involved in a project where the contractor's most important request from us as a designer for the special segments was to eliminate the need for a temporary opening frame, because the cross passages have to be treated with ground freezing, and ground freezing is in combination with temporary frames. That's a very, very difficult thing to do because of space constraints and also in terms of thermal conduction. So the contractor wanted to avoid all this, and we designed a special segments there with special high-strength shear cones and shear dowels. So there will be no permanent frame constructed first, but there will be the opening. Then we construct the cross passage. The lining design is such that the temporary opening can be supported by the lining itself, by the TBM lining itself, and then there will be a permanent frame constructed from the outside, basically from within the cross passage. The example you have seen here, the C1 example, and I believe that's now a standard approach across along the entire project, is that A permanent frame is constructed on the inside of the segmental lining and connected to the lining. And that's why these lining segments are special segments. They need to provide these connections for the shear reinforcement between the permanent frame, concrete frame, and the lining. And this will be support during the opening as well as the permanent support.
Thank you, doctor.
And Dr. Kurt, one question. Sorry, can I ask?
Yes, you can ask.
Okay, thank you, Dr. Kurt. A small question. Just I'm not clear for this because I did not heard your lecture from the beginning. What type of treatment you have given for the making it waterproof? Is the kind of hydrophilic gasket on the segment male female joint, or you had some kind of membrane behind the segments also?
No, there's no membrane behind the segments. There are two gaskets. Two lines of gaskets.
Okay, it's EPDM which swells with the water. It's kind of that gasket?
Yes.
Okay, thank you.
Hi, Kurt. I hope you're well. Sandeep here. I have a quick question for you. Since we are tunneling in fractured strata with high water levels, and we have been the TBM have been into the ground for more than 7-8 months, especially in chalk. So what has been your experience with the effectiveness of the primary and secondary grouts? Has it been effective, or have you had any issues related to that? Maybe how we dealt with them?
Not yet. Actually, we didn't have any bad experiences. It worked. The primary grouting, secondary grouting, where necessary, worked properly. There was no incident or at least no evidence that grouting didn't work. The tunnel segments are within the tolerances, aligned within the tolerances, so there's no problem there either. And also the tunnel ovalization is within the tolerances.
That's great. Yeah, sounds good. Thanks, sir.
I think that is all for for today's question and answer. I would like to thank Dr. Kurt once again. Thanks to all the members, all the participants. Stay tuned. Next month, we are planning to have a joint webinar with British Tunnel Society. All the details we will share as soon as possible. Thank you, Dr. Kurt. Thank you, everybody.
Just a very quick question. I have noted down one question for the minimum curve radius. Who shall I send this to? Shall I send this to Rushi, or Rushi, can you then distribute this?
Yeah, you can send it to me.
Okay,
and
very good.
I'll distribute it. So.
Okay, thank you.
Okay, thank you, sir. So I would like to inform all the members that our past webinars are available on YouTube channel, and this webinar will be uploaded shortly. Thank you.
Thank you very much for your attendance. Thank you.
Thank you, sir.
Thank you, sir. Thank you. Happy weekend.
Bye-bye.
Happy weekend.
Have a good weekend. Thank you. Bye.
Stay safe.